All right, today we're going to look at some trig equations that require a little bit of factoring. So just like when we've solved polynomials or any other types of equations that need factoring, it's only going to be useful to us if our factors are written as a product equal to 0. And so, that is going to be our first task here. It says, what are all values of theta on the interval from 0 to 2 pi, where cosine squared of theta is equal to negative cosine of theta? Now, what we can never ever do here is divide by cosine on both sides. You're going to lose solutions anytime you do that. If I had an equation like 4x squared equals 2x, we would subtract 2x from both sides. We would never, ever, ever divide by 2x or divide by x on both sides. That's never allowed. The solutions associated with that x are gone when you do that. So we can't ever cancel out our variable terms when we're solving an equation. Instead, what I'm going to do is I'm going to add cosine of x or cosine of theta to both sides, which makes this equation. And then because both of these terms have a cosine, we can factor it out. So cosine of theta equals cosine of theta plus 1. And since each of those factors now multiply to give us a product of 0, that means we can write each equation equal to 0. So our solutions are cosine of theta equals 0, which means that theta is going to equal either pi halves or 3 pi halves. Or cosine of theta is equal to negative 1. I didn't leave myself enough room here. And cosine is equal to negative 1 at pi. So those are the 3 places on our unit circle where the cosine takes on those values. If this is said all solutions, then we would use our plus 2 pi k notation. But this is just asking for a specific solution, so that is all we need there. So number 8 is very similar. We are being asked to find the x-coordinates of the points of intersection for f and g. And so remember, anytime we're talking about points of intersection, we're looking for where f of x is equal to g of x. So that's going to be the equation that we set up. So 2, sine squared of x equals the square root of 3 times the sine of x. Alrighty. So this is just like the other one. So I'm going to encourage you to pause your video here and try to solve this one on your own. And I'll be back in 2 seconds to work and finish this problem. So our next step here would be to subtract the square root of 3 sine x from both sides. And then I can factor out a sine of x, giving me 2 sine of x minus square root of 3 equals 0. So that gives me 2 possibilities. Either sine of x equals 0 from the first factor, or I'm going to add 3 and divide by 2 here, so sine of x is equal to square root 3 over 2. Now, figure out on your unit circle where sine takes on those values. You can use your left hand. So sine is equal to 0 at 0 and pi. Now, again, we're not going to include 2 pi because it's not included in our interval, okay? So we're using 0 to represent that location on the circle here. And then for sine of x equals square root 3 over 2, that is going to be at pi thirds in quadrant 1, and then it's also positive in quadrant 2. So we get 2 pi thirds. So we get these 4 solutions, okay? So we can always use a GCF to help us factor. Sometimes, though, we're going to get trigonometric equations that are quadratic in form. They aren't quadratic because they're trig functions, but they're going to behave like a quadratic equation. So trig equations that come in the form of AU squared plus BU plus C equals 0, where U is some trigonometric function, are quadratic in form. Again, notice the pattern. We've got a squared term, a first power term, and a constant term equal to 0. U substitution is a great strategy here. It allows us to take out the trig to make it look like something we're used to working with, and then put the U back in. Now, make sure when you are working these problems yourself, you have to make that statement of let U equal whatever it's going to be. So in this first equation, we have 2 cosine squared of x plus cosine of x minus 1 equals 0. So again, look at your degrees here. We have second power, first power, constant. That's what we're looking for. So what we can do is we can choose to let u equal the cosine of x. And again, you have to explicitly state that. If we do that, then everywhere that there's a cosine, we're going to replace with a u, and we get this equation that looks like just a normal quadratic equation. We can factor this using whatever factoring method you prefer. Let's see, u plus 1 equals 0. And now we set each of those factors equal to 0, so I get that u equals positive 1 over 2, or u equals negative 1. Now, those are the solutions to this quadratic equation. However, we are looking for the solutions to cosine of x equals 1/2 and cosine of x equals negative 1. This is where we put whatever our u was back. So cosine of x is equal to 1/2 at positive pi thirds and 5 pi thirds. And then it's equal to the negative 1 at pi. So we get these 3 solutions. So go ahead and try number 10. It is very similar. Don't forget to define your u if you're going to use that strategy. So again, pause your video and then come back here in 2 seconds for the worked out solution. I'm going to start by letting u equal sine of x. That makes my equation 2 squared 2u squared minus 3u plus 1 equals 0. When I factor this, I get 2u minus 1 and u minus 1 equals 0. So that tells me that either u is equal to positive 1/2 or u is equal to positive 1. Those are our solutions for u. Now we replace the u with what we took out, which was sine of x. So x is going to be, sine is equal to positive 1/2 at pi over 6 and 5 pi over 6. And sine is equal to positive 1 at pi over 2. Those are our solutions. Lastly is just a reminder, so we can use factoring on this one because it follows the pattern of the difference of squares, a squared minus b squared. And remember that that always factors to a plus b, a minus b. Or we can solve that one the way that we did up here. Oh, there goes my alarm clock. Hang on. Okay, and so you can use square roots to solve, but don't forget that whenever you do that, you need this plus or minus, which is why I think it is nice to go ahead and recognize that this is a difference of squares, because it will ensure that you get both of those solutions when you factor. So if I set each of these equal to 0, I'm going to get the sine of theta equals negative 1/2 and the sine of theta equals positive 1/2. So my values for theta are going to be all the places on the circle where the sine of theta is equal to either positive 1/2 or negative 1/2. So that's going to be all of our pi over 6. Pi 6, 5 pi 6 in quadrant 2, 7 pi 6 in quadrant 3, 11 pi 6 in quadrant 4. This one did not specify an interval. We're going to go ahead and just assume that it is 0, not equal to, 0 to 2 pi. Since it didn't use the word all solutions, we'll just go ahead and make that assumption. Okay, so you should be able to complete a good chunk of worksheet 1. Now you can look on Canvas for specific problems that you should be able to finish today, and I will see you tomorrow.